between the uptime, the downtime. They're going to be the same. The up velocity. So the only vector that's going to be changing in this situation is going to be your y component. At the very top, it's all x, and then it starts to cascade, and we get the y component again, and then it starts getting longer, and x, obviously not to scale, but Vx will be the same. You know, the little things to keep in mind, that Vx is constant because there's no air resistance. We're going to ignore that. And there's no gravity in the x direction. So that helps out with certain problems like your range, delta x equals r equals Vx delta t vi cosine theta, right? This is the cosine component, the horizontal. And this t is the total time because it involves the entire trip. And then with the, say, delta h or delta y, you have your v, y, I, and this is your up time because it's going up to a max height from an initial velocity in the vertical direction minus 1/2 gt up time squared. And then that up time is going to be half of the total time. Uptime and downtime are equal. Well, Vy final. And again, it's because extension of the kinematics. So this is just Vy in the vertical direction, or just throwing a ball straight up in the air. It's just Vy, but this will be Vy final from the Vy initial. Vy initial being, let's say, right here, and then once it gets to the top, Vy final is 0. There's no slope there in the vertical direction. There's no slope at all because now the velocity is horizontal. No slope. And the 0, that helps you, dissect these projectile problems very, very easily, very quickly, because you have a few things at play. I know uptime is downtime. Vy final at max height is 0. Gravity constant. Vyi minus g up time, and so forth. Vy final squared, Vyi squared minus g minus 2g delta y. So on a little bit on projectiles there. You always want to be armed in question though. You read a question, maybe read it again. Focus in on what concept is being asked. What is at play here? Is it the energy problem? Is it a momentum problem? An impulse problem? That's all in the reading of the question. Again, I don't see too many isolation vector problems like in section 4.2 or chapter 3. Now your forces and your torques. Forces are just what point masses moving x-y direction. Torques, we have force equations, and we also have that one torque equation. I'm going to do that one question and the mechanics question 3, just dissect it, just peel that apart even more, because I know we have some questions on rotational motion. So is it rotational motion specifically with the torque application? That's what I was gathering. We'll get there. And so, chapter 5, Newton's laws. The sum of the forces, then those forces that make up a total force equals 0. And this is, when this happens, you have an object at rest, you stationary sitting down, the book's on table, or it moves at constant velocity. The unbalanced forces, F equals ma. And then for either of these two situations, the net force in one direction equal and opposite the, I'll just do this to be more accurate there. F net of 2 on 1, equal and opposite forces for two masses. Newton's third law involves two forces, two masses. Again, that momentum problem, the two carts. So you just want to assimilate everything relevant for any given question, whether multiple choice or free response. Try not to, definitely try not to be too tangential, and I don't want to get off track, because then, just stay calm, read the question, and do your best to maybe jot some notes. Okay, I think it's going this way. What concepts are, are being asked there. So then Newton's laws. Questions on free body diagrams. Are we good on that? Ramps, pictures hanging from ceilings, two blocks moving under a constant acceleration. Or was it just really like the torque, the rotational stuff that was still sticky? Give me something, give me some feedback. Is this, the Newton's laws were okay? Do you need to see another example on that? Okay. Okay, we have one last one here. Okay, well, we can look back at that one. That one's definitely a bit of an ornate one. I would rather call up my previous notes on that one, because I don't want to just waste time and set up a particular question. Let me see if I can find, let me go forward and I'll come back to that one, because I'd like to see it in a real problem that I have. Okay, and so that's chapter 4. Chapter 5, actually chapter 4, old book. Chapter 5 here. In chapter 6, the centripetal motion. So, objects surrounding a curve. This is circular motion, not rotational, because with circular motion involves a point mass moving around in a circle. With rotational motions, we have an actual object spinning in place. So we are rotating the object, whether it be a disc, a sphere, or, some other misshapen object or extended object. So this is your centripetal acceleration. And then, of course, wherever your acceleration goes, at least the direction of the acceleration, so it's the direction of the force from Newton's second law. These are directly proportional to each other. And so this is going to be direct to the center, so is the force. So if this is this, then the centripetal force, or which is the net force, is going to be equal to MAC V squared over R. So the centripetal acceleration, centripetal force, always directed to the center. There is no work done by this particular force, because it's going on to the next stuff. Because force and the displacement, as it were, the linear displacement are going to be perpendicular to each other. And going ahead a little bit for the work, force and displacement must be in the same axis, whether they're parallel or anti-parallel. If they're perpendicular, there's no work done by this force, so it's going to be going around the constant velocity. It's not going to accelerate. Only accelerates if there's an outside force linear, a tangential force. And then this guy grows, gets longer and longer and longer. And then in that situation, we have a total acceleration that's going to be at some arbitrary angle. So In this case, the acceleration is all centripetal, but if we have a force on the outside that's causing this vector to enlarge, you know, get the idea. So so we have this centripetal, and then this will be our tangential. And so when we add them up vectorially correctly here, using concepts of chapter 3, we're going to get our total acceleration, which is the vector sum of the tangential and the centripetal. And we can figure out the angle by which the total acceleration of the system is projected. And by Pythagorean theorem, so a total square root of AC squared. All right, and so this is just for everybody. There was that one question on air resistance in the Physics C exam. Again, that's like literally the only time I've ever seen an air resistance question, but it's, you know, you want to definitely make sure you brush up on that. Maybe we'll have a little time to look at that as we go along. Let's see, chapter 6, chapter 7, and 8, work, energy. Let's see, generalized equation for work, cosine theta delta x, the general. And if the angle between these two guys is 0, this becomes just F net delta x, because cosine of 0 is just 1. And then obviously if theta is 180, usually that force is going to be a resistive force, force due to friction. And that work is going to be negative. That's why it's negative, because cosine of, what was I doing here? Theta equals 180, minus 1. So cosine of 180 is minus 1. That's why the work done by friction or any resistive force is always negative. It takes energy out of the system. Work is the change in kinetic energy, which is also equal to net force delta x. So depending on the type of question, or you read a question and you know it's a work energy situation, this is a force over the displacement, blah, 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 how fast is this object going, blah, 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 how much kinetic energy does it have, what's the acceleration in the system. The concept begins here, where in order to find, say, the acceleration, you'll have ma delta x equals to this, and you can find out the acceleration. So it just depends on the scenario. But don't ever lose the concept, because this is where you're going to start. It's like half the battle or whatever. That it's always focused here, and that will allow you to get your final result once you put down the correct concept. What about that situation do you not understand? Just, well, so, all right, hold up. So again, it's concepts. We don't want to get caught up in maybe the final result. We want to dissect it bit by bit. Going back to, we're going to get to the 2 blocks and all that. We want to just make sure that we can, we want to diagram all the forces acting on each object in the system to get, say, an acceleration of one block versus another one, or in a situation, or you have two blocks attached to a pulley. you want to, diagram the forces acting on each one. So if you are in an elevator and you have normal force like this, and you have weight going like this, and you're going up, it's, this guy's going up. So you can find out what the normal force is just by a simple free body, like we have there. So let's say Fn minus mg equals ma, and if you find acceleration, you can, or find a normal force, you can, right? Because then in this case, the normal force is going to be just the sum of ma plus mg. And that's why you feel heavier, because now you have these two forces here. And then in the opposite case, you can say in that case, I always like to keep this positive. In the opposite case, you're going down. So all the forces that's moving with the acceleration must be positive, and Fn is going the opposite way, that's why it's negative. So now we have a situation of, Fn equals mg minus ma. So you feel a little bit lighter. So that's just the core. Now, of course, different problems. I want to solve for this. How much time is it going? What's the speed? Those are dominoes. This is the first domino. The concept is the first domino at all times. Does that make sense as far as the first approach? Or do you have another question regarding that? Okay. So yeah, the key idea with any forces problem, you want to always diagram the forces acting on each object in the system. There is nothing mysterious about that. In order to find, certain things, a normal force, time, whatever the case may be. Okay, so we talked about work, kinetic energy. Also in the vertical direction, we know that the work done by gravity, most typical situations, is equal to the negative change of the gravitational potential energy. We are losing potential as force of gravity does work. So this is being lost and converted into kinetic energy, which goes back to the original idea. Work is change in kinetic energy, which is also equal to negative change in potential energy. And when you add those two guys together, the sum of the changes equals 0. We're just converting energies back and forth. The work, the amount of work done by gravity will be the same in either case, whether you're losing or gaining, whether the signs switch. That's why the total energy in the system is 0, because negative one way and positive the other way add up to 0. And in this case, you're just falling down. You're losing potential as it goes to the Earth. If the Earth is going to be your 0 reference, you can make anything 0, your starting point, your 0 reference. That would be the conservation of energy. And in the other case, if there's friction, and this should be technically the sum of all forms of potential energy, because there's a spring energy that could be there. And that equals the work done by friction. We call all forms of friction, like air resistance, the work friction. And it's usually mu k Fn delta x, because force times displacement is work for any force. This was conservation. This is non-conservative. So they go and talk about the relationship of conservative, non-conservative. Well, friction's a non-conservative force. You're going to always lose. Gravity, the electric field, the magnetic field, those are all conservative forces. Magnetic force, electric force, gravitational force, conservative. You always get back what you started with. Some of the changes is zero. A nice example of the magnetic force being constant is in Faraday's law of induction, but from a tangent on that. Let's see, I'll just doing everything, Phys 1 and Phys C, fit, and then on that if you need to. The power obviously is going to be the rate at which you're using energy. This is the same as this. And any forms of energy, whether it be kinetic or potential, that's just work over time. Power measured in watts. Momentum. And conservation of it. So the sum of P1 and the sum of P2, whether there's two masses, could be n number of masses, any number of masses equals zero, much like the energy principle right there. So again, I'll just write it up just briefly. P2 initial M1. And that's conserved. Momentum's always conserved. Energy is only conserved in an elastic collision. And energy is not conserved in inelastic collisions because some of the energy is going into the deformation, the sound of the connection as they roll along. So, heat, sound, light, whatever, deforming of the vehicles. So some energy is lost. But energy is always saved elastic. And then, most of these equations you'll see on your equation sheet. I would take I review them today. I would definitely take a look at them the day of to simulate them. So that would be the inelastic collision case. And energy is not saved in that case. Any questions regarding that concept? So what I want to do here at this point is, I think I'm going to go to that one example. So in rotational motion, we have objects that are spinning about an axis, usually if the central axis here. And so we can idealize this as a unit circle. And so angles are changing, they're going around. Okay, so we have, say this is theta 1 and theta 2. So this object spinning counterclockwise, it can spin clockwise. Yeah. So you can just imagine this as an object. And so in this case, we have this This linear distance we call the arc length. But in terms of this object rotating through 2 pi radians, and we'll call 2 pi radians 1 revolution. Let's say this object has angular quantities. It has angular displacement, which are the thetas, not linear. The linear displacement will be the arc length. S equals r theta. This is the angular, this is the linear. V equals r omega. A equals r alpha. So there's a transformation from linear to rotational by way of this radius. We are taking that point mass and extending it. It's really like a power series. Point masses becoming this rotational shape through a radius. That's the transformer from linear to rotational. And so we have our velocity now is married to angular velocity this way, and then linear acceleration and so forth. So those are the basic formulas for the linear to angular. So theta is S over R, and omega is V over R, alpha A over R. And so when we get to torque and we see it is I alpha, we know that alpha is equal to A divided by R, that sort of thing. Then the rotational kinematics. So all of the linear stuff becomes a rotational analogs. Linear kinetic energy becomes rotational kinetic energy. There is no rotational potential energy. It makes sense. You're not rotating. Potential energy is function one to one height. And we go from mass to what we call a moment of inertia. So if an object is a rotating object is losing potential energy, its center of mass is losing potential energy. It's not rotating through a loss. That's why it's still going to be mgh for rotating mass or an extended object, or some object other than a point mass. So moment of inertia is just a distribution of mass over a radius. mr squared for a particular object, a hoop, a disk, 1/2 mr squared. Different shapes have different moments, and they usually give those to you. And you can derive them through certain techniques of integration to get to all the moments of inertia if you wanted to do that. Center of mass, that's, some with relative to some reference point, some starting point, you can get the center of mass of a system of point masses or a center of mass of an object. Now, center of mass of an object, you have to, do a little integration for that. But, that's out of the purview of Physics 1 and pretty much out of the purview of the Physics C. I don't see us having to really be worried about that. But center of mass, radial center of mass, which is a combination of X, Y, and Z. So, you can repeat this for Y. It says this center of mass in X direction, center of mass in Y direction will be MI, YI, and ZI, and then radial center of mass, which is like this large, hypotenuse for X, Y, and Z axes. You just add them all together. And it's not a vector, these are points. That's why you just add. Just let me know if you have a question on anything. So the basics of rotational motion, the kinematics, all the stuff, I don't want to write it up, delta x becomes delta theta, v becomes omega, a becomes alpha, and all the kinematics equations. And depending on the scenario, you can use those to find out, oh, what is the angular velocity at the end given such and such and such conditions, you know. It's all about, okay, I know that this object is rotating. What is the difference between circular motion and rotational motion? Circular motion involves a point moving in a circle. Rotational motion is these spheres and disks and rectangular planes spinning. That's all it is, because you're going to see that point mass systems, that stuff in chapters 1 through 8, well, all that stuff deals with point masses, and then when we get to rotational masses, we're just taking that point mass and we're blowing it up. It's like we're looking at it through a microscope. Okay, here's point mass. Now it's a large mass spinning. Point mass could be a shape. It could be a rectangle. It could be anything. So we just deal with it as a point. But then we either look at it through a microscope or we blow it up in a power series, and we have this, you know, all these points making up this shape, rotating about a common axis, usually the center of mass. And then we can rotate about any other axis. We don't have to rotate it around just the central axis. And so that brings me to the next idea, where we have moment of inertia, say of, then I'm going to get to that one question too, because, you know, they did a little bit of sleight of hand. Anyway, this will be a moment of inertia of a hoop, and a disc will be, you know, let's say they usually give this to you in that one question. They didn't, so it's like kind of had to do some inference maybe to get the answer. 1/2 mr squared. Now that's about the center. Common, easy. Oh, I want to do it over here. Well, the parallel axis theorem, right? I want to get the new moment of inertia. I'm not going about the center. So, and the basic conceptual reason is, now if I spin it here, this axis is seeing the mass distributed differently. So we're going to have a new moment of inertia. This is the basic idea. So moment of inertia is going to be the original, well, they usually say ICM. You always want to start things off with an easy reference point. Yeah, same thing. Plus md squared, because now you take the mass and you go into a new distance d, and this is parallel axis theorem. So like, imagine two axes coming at you parallel, you know, through those points. So that's just, you know, the basic idea there. I've seen questions, well, okay, this object has a moment of inertia this, or if I move here, what's the new moment of inertia? So parallel axis theorem. You know, it's all about, what is that question trying to say? What is it asking me? Here's the question. What concept do I need to get the right answer? Yeah, there's going to be some nuance always. You want to test your understanding. You're not going to be, it's like somebody made a good analogy. Like somebody can go to a gun range and get off 2,000, 200,000 rounds, you know, shoot. But in a scenario, a real life scenario, how are you going to take that training, maybe that gun range training and a little bit more, and be able to survive or get, you know, use it in a real life situation? You have the ideas, you know what to do, you have the concept, you have the training. So now you have to remember that and execute it in a nuanced situation. So you're gonna probably have, you know, remember those problems where we had the string and the object was rotating like the yo-yo? the concept is, okay, I got to get my free body diagram on that thing, and I got to get a torque equation, which I'm going to go now to my that question before I forget. And Emmanuel, as far as the 2 blocks, I will refer everybody to the video that goes over that, because I don't have time to do it here. But yeah, you can definitely look at that again. It's search it out. That is a very good problem always. I continually use that one. I just want to stay focused and here for a moment. But I'll give you the reference. Search the video out and you can take a look at it. Any questions on angular momentum? Well, one thing I want to do is, oops. I'm gonna call up the physics C question, and I'll talk about that physics one, the one with the oil, because yeah, they do oil. They're gonna have little graphs and all this wordiness, but it's a conservation of energy problem. Knowing that going in, you can now have confidence and attack it with some with some force. It's all about knowing what's conceptually going on. Yeah, this guy. Whoops. Let me share. Okay, so this was that question. I saw that maybe a little bit of issue, and also goes to your questions about the rotations. If I got your question right, we still needs some more practice with the rotation stuff. Got the pulley. This is similar to a skills test that I gave, but this was much easier. I mean, in context, but the concept is the same. So in this situation, we know it's rotational motion problem. We have to. So what's the method here? What's the method with these type of questions? So method for rotational problems is there's going to be, well, there's no particular order, but draw your free body diagrams. You got a pulley. A pulley's got a mass. That small pulley doesn't have any mass, but the big one does. So you know that there's going to be some moment of inertia kind of stuff in there, because we've normally, back in the day with FBDs, we ignore the pulley. It's a point. Ignored. But now when there's mass in that object, it's a rotating object, so it has rotational motion, it has moment of inertia, we can't ignore it. Draw a free body diagram. And there's going to be a couple of forces. There's going to be force equations, and there's going to be a torque equation. But the first one, it says, okay, well, that data, we never did an experiment like that, but experiment at all. I mean, outside of the Lapster. So the data points are doing that, but you know that there's like a best fit line that you can make, and acceleration is, and again, this is approximate, because 1.5 minus 0.8, 0.53 minus 0.3. That comes out to be roughly 3.04 meters per second squared. It's slightly different than the so-called answers, but listen, if there's this degree of uncertainty here that will be allowed, because you can't tell exactly that point. They're not going to ding you for that. So this is fair to report something in this around this number. So the second thing is we want to draw a free body diagram on that falling mass. So we have negative tension here, and then we have mg. Why is that negative? That's negative because, you know, ma is this way. It's going opposite the acceleration. So our force equation will be mg minus t equals ma. And then we have a torque equation. We have a torque that is provided, that is acting on that rotational mass. So from this point of view, I'm looking at the bird's eye point of view, and I have a string going like this. This force over this radius, which it, you know, they give you the radius, that's going to produce a torque. That's going to cause this thing to accelerate, have an angular acceleration. It's going from zero angular velocity to some final angular velocity. So it has an angular acceleration and has a torque. What causes things to have an acceleration? A net force. What causes things to have an angular acceleration? A net torque. So torque is the rotational analog of the linear force. And so again, in this case, is the force provided by the tension, and this will be TR. And then we also know, let's see, net torque. TR equals moment of inertia times alpha. It looks like ma, except this is a distribution of mass about some center or about some axis of rotation. So, and they want you to find the moment of inertia of the deal. So we're looking for this. We got to find this first. We know what radius is. Do we know this? We can find that too. A divided by R. Okay. So just in context, I'm going over that, you know, that question and hopefully addressing the concerns of rotational motion. Is this what most people had a question over this forces and the torques, how to use both of them at the same time? Yeah, I mean, I think a few other people had that. But yeah, it's see, method is free body diagrams are always. There's forces here. You have to get a free body diagram in order to get your force equation or equations. Then after that, there's an additional equation. There's a torque equation. Why is that? Because now these pulleys have mass, and so we have to consider the torque on those masses, those rotating masses. So let's get the tension first. Tension is going to be mg minus ma. If you just, you know, rearrange this here, and then you plug in your numbers, 0.05, 9.8 minus 3.04. Again, slightly different from theirs, you know, again, it's trivial. Like saying the difference between 3.04, okay, so they get 3.01. Yeah. As long as like you're not getting 10 here, that's a problem. So the tension will be 0.338 newtons, and now we can plug it into here to get this. We have our acceleration already from part A. So then this becomes TR. So now, right, so IA over R again, and this would just be, you know, you multiply R to both sides, TR squared over A, right? And then that'll just be the 0.1 squared. That comes out to be, let's see, 0.0011 kilogram meter squared. They got 0.0013. Who cares? It's irrelevant. It's all in the guesstimation of that slope, you know. It's off a little bit. off is relative. So that's the moment of inertia of this rotating pulley. And then moment, that's why I was saying angular momentum. Well, there's two equations for angular momentum. I omega, this is for a rotating object. And then this will be for a point mass, MVR. Because this situation, we have an object moving around a circle with a particular momentum, because we know that this is velocity and this is a mass, P equals mv, and moment of inertia is the cross product of momentum and the radius. So the MVR, MV cross R, R cross P, technically, we are curling the radius into the momentum. We can get into all that. MVR. So those are equivalent. This is for an object. This is for a point mass. But still, for either case, gives you angular momentum. So since it's a rotating object that we want the I omega, and then I can get the angular momentum. And then omega, we don't know offhand, but we know that omega is V over R because we checked our equation sheet. We could see that V equals R omega, and omega is V over R. And that becomes 0.0011, 1.25 over 0.1, and then that equals 0.01375 kilogram meter square per second. I don't know if they ding you for not having the units of angular momentum anymore, but I would put down, I would be explicit everywhere. When they say justify, give it all. Don't hold anything back. Explain, use equations, concepts, be coherent, and giving all your justifications. So that's angular momentum. And then, oh, and the next question was, the disk is removed and replaced with a hoop of the same radius. Mass and radius, but with all of its mass concentrated near the rim of the hoop and connected to the axis by lightweight spokes. The experiment is then repeated. Is the angular acceleration of the hoop greater than, less than, or the same as that of the solid disk? So we have to know the moment of inertia of this hoop. And the moment of inertia of the hoop is greater than the moment of inertia of the solid disk. So in this one, it's kind of like we'd have to know the difference in the moments. I mean, so that's why I was, usually they'll give you the moment of inertias, but the hoop would be greater, so the angular acceleration is going to be less. That's why it's less than. Because in this equation, let's see, small inertia. So TR I alpha, so then TR over I. And so the moment of inertia of the hoop is MR squared. The disk would be 1/2, so this is greater, so this alpha would be less. Let me jump over to the physics one, the oil problem. Oh, okay. Okay. It's kind of weird there. Okay, so now say you get a situation like this, you have this graph, you have this weird looking curve, you have the picture. Do not lose your cool, or any other situation that may seem unfamiliar, because you're going to get all that you need in the question. Food scientists have created a new oil. At room temperature, the oil is a liquid. As the oil gets colder, however, it stiffens, thickens into a sticky gel. To explore the properties of the oil, the scientists fill a container with the oil to a height d, as shown in the figure above on the left. They drop a small steel ball of mass m from rest at the top of the oil. Using video to capture the ball's motion, the scientists calculate the energy lost. Yeah, that happens. You don't want any mistakes, but and that's an understandable one. You have to read it all the way through. Using video to capture the ball's motion, the scientists calculate E lost, mechanical energy lost by the ball Earth system from the time the ball enters the oil to the time just before the ball strikes the bottom of the container. So it stiffens up, it gets thicker. So it's going to get slower as it goes. So we can see kind of a gradual increase to the maximum energy, but that's maximum energy lost because this viscous medium, this oil, is taking energy away. And it's gradually going to take it all the way to zero. It's going to gradually take it all away, so the object's going to come to rest. But it's gradual. Kind of answering the questions already. The scientists also defined the stiffness S of the oil as a quantity proportional to the force required to move a rod through the oil at a standard constant speed. The scientists calculate E lost and S at several different temperatures, ranging from room temperature to the lowest temperature at which the ball still falls to the oil. The graph above on the right shows E lost as a function of S with the calculated data points and a best fit curve. Best fit curve because the data is nonlinear. And we have the proportionality between E and S. So it's good to have data, charts and graphs. Give a physical reason why the curve in the graph would not reach the vertical E lost axis, even if the scientists had taken data over a broad range of temperatures. Again, it's the oil, different. Again, that's reasoning. You have to, one thing you could say is that taking a long time because of the viscosity of the oil changes as it goes through. It gets thicker and thicker, so it's going to get slower and slower, but gradually, right? And eventually it will have all the energy out. It will have the energy lost, but it's taking a while. It's gradual. So you just put an equation in there, the energy loss, which is equal to negative mass GD. That's the second question. So yeah, the viscosity changes. It gets thicker and thicker. And so the speed is going to gradually decay. And we see that gradual decay reflected by this graph. Something like that. As S increases, the thickness of the oil, E lost approaches a maximum value. Write an equation for E max in terms of MD and physical constants as appropriate. Well, friction, or the viscosity that's causing this friction in the oil, is causing a loss in the potential. So it's really as simple as total E is mgd, the potential energy, plus the kinetic. The kinetic is, we can say that at some point, we know at some point it's going to get so thick that it's going to be, it's not going to be moving anymore. So no kinetic energy at that point. As T goes to infinity, E is reaching a maximum. So this kinetic energy term, even though this is the concept, doesn't really apply. And also, it doesn't even you know, factor into the question. They want you to write an answer in terms of mg, md, and physical constant. And that's the only one here is mgd. You can write this to say, oh, that's the magnitude of the energy loss, and this is just how much energy is lost. This is more accurate because, you know, this is being lost out of the system. Oh, I didn't share that, I don't think. So this is what I was doing. MGD, this, you know, this doesn't really apply. It eventually comes to rest, and that's your equation. And you know, you can see that the answer's there. I'm just talking through it. Justify. And then justify, you want to justify with an equation, with an explanation. One of the scientists in trying to represent the relationship writes down the equation E CS squared. It should be, where C is a constant with appropriate values. Another scientist points out that this equation cannot be correct. Give 2 reasons why the equation cannot be correct. The premise is not correct. So one thing I said, and again, you're not, I don't think it's going to ever be 100% of students that are going to give the answer that a reader is thinking about, because the multiple answers could work. You just have to justify it. So what I said is that this is a right side up parabola, CS squared, and we see that this is trending, you know, to an asymptote. So that equation doesn't work, you know, just based on, you know, the mathematical nature of that graph. And then also, this graph doesn't have a negative sign to indicate that there's energy being lost. It's a magnitude. It could be, you know, a function that describes a magnitude of the energy loss, but, you know, whatever reasons you give, just be explicit in your explanation, and they're pretty lenient about that. As long as you know what you're talking about, what you talk on the concept. Again, it goes back to concept. This one, letter D, I can't see it. It says T equals Z over S. Further attempting to model the ball's motion, the scientists write the following equation for the time the ball takes to fall. Is this equation S plausible? In other words, does it make physical sense? Well, you can see your example answers. Well, S is going to get thicker, and that means that time is getting shorter. So it doesn't make sense just based on that. It's not plausible, because S, we know already from the premise that it's getting thicker and thicker as it gets colder, and you know it's going to get colder as it goes deeper into the oil. So that doesn't make sense. It's not plausible. And then lastly, changing kinetic energy. So we know that okay, I think you can see that. So the potential energy change is like this. So kinetic energy is going to be the reverse of that. So where there's mins and maxes here is the opposite for the kinetic. So it's going to be like that as C. So this 0, it starts off very fast, but slowly as the thickness increases, it gets to 0. And this gets to a maximum loss. On the axis below, sketch DK. Sketch me as a function of S. Sketch the kinetic energy as a function of the thickness, the oil stiffness. So we got that. And yeah, so we're out of time on that. Okay, so we have a minute left on that. So I just wanted to just kind of talk through some strategies as you get ready to take the exam Wednesday. I think you You guys will be fine. You guys have done this, you've been practicing, you're gonna be good. So that's what I want to do. But from what I can tell, you guys are looking at all of these, been practicing all these different scenarios, and should be good. I'll see you again on Wednesday. So yeah, any last questions? Grades and stuff. It's going to be on kind of purely subjective basis. I'll just look at overall your practices. Your practices look great, and finals and all that good stuff. But yeah, I have confidence in you guys. I have belief in you guys. Go ahead and take care of it. Take those strategies, take those concepts, and see you again Wednesday. So if there's no other questions, I will let you guys go. And oh yeah, I'll post up the video, Emmanuel, so you can go over that again. I felt, so you can review those 2 boxes scenario. All right.
See you, Mr. Kelly.
See you later, guys.